In our last episode, we explored the similarities and differences between the world idea from Haskell's Gloss library and the environment of OpenAI Gym. We designed a Haskell type class to capture this idea of an environment that could use associated data types connected for the specific game that we're playing. Now, this week, we're going to show this class in action. We're going to take our toy example of using BFS to search through a simple maze, and we're going to make an environment for this game. We'll see how all these details fit together, and we'll see the game play out in our console. There's also a special announcement at the end of this video if you're interested in AI and machine learning, so make sure that you watch to the end so that you don't miss out. So let's get started. I may sound like a broken record at this point, but we're going to start by defining our types. First, we will make the state type for our environment, which will be functionally equivalent to our previous world type in Gloss. This state isn't the object of our class, though. In order to do that, we have to build a monadic type. So what monad should we use? Well, naturally, the state monad stands out as a good option for us because we want to track this stateful type. Seems pretty obvious. But we'll also include I/O on our monad stack so that later on we can render our game. So let's also go ahead and define some basic monad instances like monad state and monad I/O, and this will make our life easier when we go ahead and write our implementation code. Before I go any further, I'm going to define this direction type. This is going to serve as our action type a bit further down. When we consider the options that we have when moving in our maze, we can move in any of the 4 cardinal directions, up, down, left, or right, or we can make no move at all. So let's just quickly define an enum type to represent that. And now we're ready to go ahead and start making our instance. So the first thing we want to do is assign the associated types. So remember, we have an observation, an action, and an environment state type. When it comes to the observation, the mutable data of our game state is just a player's location. So we can assign location as the corresponding type here. For the action field, obviously we'll use the direction like we just described, and we'll use our state type above, maze game state, and that'll be the environment state type. Now we can start filling in the functions and expressions for the instance. So resetting our game is a fairly easy function to write. We just want to change the player's location to the start. So we fetch our current state with get, and then we put a new state where we've modified the player's location back to the starting location. Easy enough. Running the environment is also rather simple. Given an action in our monad, we'll unwrap its state action, run that with the given environment, and produce the I/O action. After that, getting the current observation is as easy as querying for the player's location out of our environment state. And then for the possible actions, we'll just return the full list of enum values. If we wanted to get fancy, we could remove the option of moving into walls and moving off the board, but we'll need to handle that logic anyways later on, so we'll keep this part simple. We have just one field left, but it's also the most complicated. We need to determine how to step the game forward based on an action. And so this will always be the toughest part because this is where all of your game logic really happens. Our game is pretty simple as far as games really go, but we're still going to want to start out with a few helper functions that'll just make our lives easier. So the first of these is we'll just determine if a space is a valid move in our grid. And this is fairly straightforward. We just want to check that the
location, row, and column is in bounds for our grid, and we want to verify that it's not a wall. So we just have to check all these different conditions within the bounds of the array and check what's actually in the array's space. Make sure it's empty and not a wall. Now we want two functions that are kind of inverses of each other. The first of these, find next location. This will take the current location and the direction, and it will give us the next location. So this also just fairly straightforward. We have to do essentially some case logic where we consider all the different directions that we're going to move, and if we're moving up, for instance, that's going to reduce the row value, say r-1, but same column. Moving left, we reduce the column value, but it's the same row, and so on. So again, another straightforward function that just sort of accounts for these different cases of our enum. The next function is move direction. This will do the opposite. It will take two locations and tell us, okay, which direction do we have to move in order to get from the first location to the second location. And again, just pretty straightforward conditional logic. We'll consider all these different cases for the different directions we might move. And if none of them really fit, then at the end we'll just put move none, because it's essentially an illegal move. Now we're ready to write our step function. Recall that this function will take our game's action, which is a direction we desire to move, and we'll start by retrieving the game state and the current location. Now we can find the next location based on the direction that we're stepping in. If this is a valid move, then we will end up assigning it as our final location. But if it turns out this wasn't an invalid move, then all we really need to do is just say that our final location really is going to be the previous location. Regardless of this, we'll then use the put function to update our state with this final location. And once we are done doing that, we then need to determine our return values. Of course, the final location will provide the new observation that we want as the first part of our return value. But then we have to figure out, okay, are we done? And that's simple enough. We just take our final location, and if we're at the end location for the maze, then we're done. That's how simple it is. For our reward, if we are at the final location, if we know that we moved to the final location on this move, and that we are done, then basically we will give a reward of 1.0. Otherwise, we'll just give no reward, say 0.0. And so this is just a very basic reward structure. And so we can then return all of our different values. And now to play our game, we need to supply a brain. That is, we need to be able to choose an action based on the game state. So we'll call this function choose_move_maze, and it will just produce a direction based on the current state of the maze. And we're just going to start this off by retrieving our environment. And now with access to the game's grid and the relevant locations, we can turn to our trusty breadth first search function, BFS search. So that takes our grid and the current location and the end location, and will supply us with a path. And we'll just do a case statement on this path. If there is no path, if it's the empty list, then our direction is just none. We can't really make a productive move. Otherwise, if we have a non-empty list, we have a first item in that path, then we'll just return the move direction from the player's current location to the location that the move represents. Remembering that BFS search, it returns a location or a list of locations as our path. And so that's all we need for our choose maze move function. Now we can play our game. We'll go ahead and build our code, and then we'll bring up GHCI and just make sure that's working, and we'll create a basic environment using some simple default values like we've been showing. 0, 0 is our start, and the player's current location. 2, 2 is our endpoint. We use base grid, that's just simple grid. And then we can use our game loop function that we talked about last week in conjunction with the brain function we created just before this part. And look at that, it produces our final location 2, 2 and a reward of 1.0, indicating that we reached the end of the maze. So this is great. We can now play our game in theory, but in practice, we'd like to be able to see what is going on. So let's make a render function and make our environment renderable. Let's start by defining an ASCII character to correspond with each type of location in the game. This is a fairly simple function to write. It'll just be, a series of if and else statements, nothing too interesting there. And now let's go ahead and actually make this renderable instance and our render end function. To start this function out, we're going to want to divide our grid, our array, into its constituent rows. And the group by function is the easiest way to do this. We use the first element of the tuple index to do this matching so that we get all of the rows together, all of these items whose location has 0 as that first element, and then 1, and then 2, and so on and so forth. And once we've got our rows set up, it's simple enough to just do a nested loop and then print the character for each cell of our array. Once we're done with that, we can bring our game up in GHCI again, and we'll do the same thing we did last time. We'll create our base environment, and this time we're just going to use game render loop instead of just the normal game loop. And once we kick off that function, we'll find that it displays the game at each stage so that we can see our player moving along, navigating with the breadth first search. So we can see it goes along the top row and then down the right column and then into that final finish slot.
Now, the only thing cooler than making a game with a working AI is having that AI learn for itself what to do. And next time we'll modify our environment so that it can use machine learning to improve the agent's behavior over time. We'll use a simple reinforcement learning approach to help our player navigate this simple maze. If you've made it this far, you deserve to hear our special announcement, which is very much related to the idea of machine learning. One of the most important technologies when it comes to machine learning these days is TensorFlow. But as with OpenAI Gym, TensorFlow support is mostly in Python, not Haskell. But there is a Haskell library for TensorFlow. This does exist, and today we're releasing a new course called Haskell Brain that will help you learn how to use this library. It goes through the basics of getting set up with Haskell and TensorFlow on your machine, as well as the conceptual and syntactic ideas you need to get started writing your code. So if combining machine learning and Haskell sounds like a thrilling idea to you, then head over to our course page now, which is going to be that first link that you see in the video description. Hope to see you in the course. You don't want to miss this one.